For the uniform distribution, we use, let's say, R unit. So this is a uniform distribution, all right? Okay, so R unit is uniform 0, 1, right? By default, okay? So if I want, let's say, 10 numbers, I need to just put 10 over here and run it. Of course, we all get different results, but the key thing is that this is a probability distribution. We are going to get probabilities because it's between 0 and 1. Is that okay? So that's it. Okay, so it means that if we want to write this exponential function, we will need, instead of putting in p, I'm going to put in the sample size. Is that okay? Because I know that I can then use the uniform distribution to generate the number of observations that I want. Okay. So n, and then the rate is lambda. So let's put lambda like that. Okay. Then we open, before then, in R, a function will have name, then this, then we have function, then we have argument, then we have this is the body of the function, and then usually we return result. So that's the sort of structure we are using. Is that okay? Name of the function is my x. We have the keyword function. Argument is the sample size and what? And the lambda. Then we're going in there to now get the quantile. Right. So here I can then generate P. What is my P? My P will be the uniform generation of the random numbers or the probabilities from a uniform distribution. So R unit, then I can just copy this and paste. Of course, we can just put the sample size because by default, the min will be 0, the max will be what? 1. Is that okay? That's the default. Okay. So I can just put in n. And that will generate observations from the uniform distribution. You can try by deleting this and then you run it. Whatever it is, you get this. Sorry. Whenever I do this, I run this, I'm going to get numbers between what? 0 and 1 over and over again, like that. So that's it. That's the default. But if you want to write it in full, then you need min and max. Meaning we can also generate observation between 0 and 10 and what have you. Okay. So, so maybe n is equal to n. That's fine. And then I need to write this. So how do I write this? 1 over lambda times log of what? 1 minus p. Okay. So I'll say that QP is assigned 1 divided by lambda times. So you have to log of 1 minus what? P. Oh, I forgot the negative. Negative. Okay. So with this, what do I need to return? I need to return what? QP. Okay. So this function should generate exponential random variables for us. Okay. So let's see how it works. So first, I'm going to generate let's say I call this ESP sum. So let me just put my n is, let's say, 10 or 100. Let me put n is 100. And then lambda is the rate. So let's say 2. So let me take 0.25, meaning my mean will be what? 4, right? Okay, good. Now, so I'm going to use the exponential random variable. N is equal to n, rate is equal to lambda. So this, sorry, I need to run this before. So this is going to generate random numbers from the from the exponential distribution. Okay, and if I want to see the exponential curve, well, I can use what do we call it? No, increase the sample size, right? Okay, so let's see how this looks like. Yeah, okay. I don't need the main, so let me take it off. Okay, so like this. Okay. I can go back and redo it and so forth. Okay. So there it is. We can check the mean of the sample. What do you think it will be? 4.2 something. Okay. If I increase this to, let's say, 5,000, the mean gets closer to 4. What kind of principle am I displaying here? Yes. Let me start from 50. The mean is 4.6. So I increase it to 500. Let me just display. The mean is 4.11. What will happen when I get to 5,000? 3.95. Now, what kind of principle am I displaying here? Who can explain to us? From your probability. When I increase the sample size, what is really happening in there? You are lost. Okay, so let me give you another assignment. So your assignment is that when you go, you take n, you take the mean, you can even find the variance. So the variance, okay, so you generate observation from exponential.
Sir,
yes.
what about the principle of law of large numbers?
And now that you are saying it, I've already given you the assignment. Okay, so exponential. Then let's take normal distribution. So we are looking at the law of large numbers, right? So what I want you to do is that choose your own sample size in increasing format, right? You can take a parameter from the exponential distribution. Once you take the parameter, you know the mean, you know the variance, right? Okay, so you increase the sample size and then find the mean, find the variance, check with the theoretical values what is happening. Is that okay? That will demonstrate those concepts you were doing in probability. And you can also demonstrate the central limit theorem using the same principle. Is that okay? Is that okay? Yeah. Good, okay. So that's your assignment. Please do it nicely. You can get your parameter. So this mean will have its parameter relative to the distribution you are dealing with. Maybe we should add gamma, right? So number 3 is gamma distribution. Each of them. Please do so. Okay. And then you tell us what principle in statistics you are demonstrating over there. Okay. Later on, we get to consistency as well. So when you find a mean square error, we'll check whether which one is more consistent, like you were doing in 333. So you were able to actually calculate and say this one has a better relative efficiency than the other. You can demonstrate it in R as well. Okay, so let's move on. So that's from the main distribution, but our own, what about our own? Random number generation. Or random variate, that's better. Our own random. So we need to now go through the same stuff, but instead of generating from RSP, we are going to generate from what? MySP, right? Good, okay. So let me bring it here. So the first one, so maybe I call it my sum. It's n and what? N and lambda. So n is equal to n, lambda is equal to lambda, right? Good, okay. So the first one, let's start from 50. So we generate this one. This is the, so we can also come here and generate as well. So this one is my sum. I hope you follow what is going on. If you don't, you draw my attention so that I explain. So you see, it's also following exponential, right? Okay, but what we were doing was that we only pass in all lambda and n. We've not specified any exponential. What we did was to go through it through all the quantile function approach. But we realize that the variate we are getting is of exponential form. Okay. So let's see the mean. 4.66, 4.26. Our own was, but they are random numbers. So you don't expect to get what? The same number. Okay. So let's go on again. Let's increase the sample size to 500. As for this, we already know that the function. So I'll just jump to our case. Okay. So you see the exponential curve is now profound, right? Then you see from 4.66 we get to what? 3.91. What is our mu? It's 4. Yeah, so we are getting closer to 4 as we increase the sample size. Let's go back and increase this to 5,000. So I'll come over here, generate the observations, plot it. It even signifies an exponential distribution even quite well. Okay, then we find this 3.94. So as we keep on increasing the sample size, our parameter or our estimate get closer toward the parameter. Okay. Any question on this? Any question? So that's how you get the quantile, or you generate observations using the, so if it's 50,000, we even get this more. And we can actually fit the exponential distribution and superimpose the curve on it, just like we did yesterday. Any question on this? Okay, good. So then I can move on. We have some few minutes. Now, you remember, so now that we know how to write a function, we know how to generate moment estimators. Is that okay? Because in your 333, you talked about moment estimators. So if x is exponentially distributed, what is the moment estimator for the parameter gamma or lambda? If x is exponentially distributed with parameter lambda, what is the moment estimator for lambda? the moment estimator for lambda? X is exponentially distributed with parameter lambda. What is the moment estimator for lambda? It's lambda. My friend. Yes.
So 1 over x bar.
If you don't know, then it means you get more assignments.
So 1 over x bar.
1 over
X bar.
1 over x bar. Okay. So lambda curve moment, you say it's what? 1 over x bar. You say it too. Okay, what about maximum likelihood?
So the same thing.
It's the same. It's the same. Okay, 1 over x bar. Okay. Now, what about x is gamma? Alpha beta. What are the moment estimators for alpha cap and then beta cap? Moment. Moment. And then beta cap MLE. So let's say ME is MLE. MLE. Yes. What are the moments and the, if you have forgotten, you have Google in front of you. Okay. So let's go on. But what is the principle behind the moment estimation? What is the principle behind the moment estimation method? Yes. Yes. You use sample mean. Okay, so what is the general principle behind the moment estimation method? Using the sample. Speak up a bit. Choose your words well. You are in the statistics department. Yes.
We want to show that the sample parameter is the same as
Sample parameter.
so the sample statistic
Yes.
is the same as the moment.
For the moment. So the principle is that the sample.
You equate the samples.
What really do you equate?
The expectation and then the variance.
So what is the general principle? It can't be the moment, it can't be the mean and the variance alone.
To assume that the sample statistic is the same as
You are still repeating the same thing. There's something. Sample what? Yes, close, but still, there's a word you need to. Sample, yes, that's it. So the key thing is that there we assume that the sample moment estimates what? The population moment. So if we have three, if we have three parameters, then it means we need the first moment, second moment, third moment. Because you need the same number of equations to be able to solve for it. Okay. So for the exponential, we only have one. Right? It's just one. So the first moment. So what are we going to do? We are going to say that the sample moment, that this sample moment is the same as all the expectation of it. But since x is this, we know that our expectation will be all 1 over 100. So we make lambda the subject, put a cap on it, and that becomes our moment, which is 1 over our x bar. Is everybody okay with it? Okay. So in this case, all we have to do is all we need to do is to write a function that will just invert the first moment, or the mean, sample mean, and that gives us our moment estimate. Is everybody okay with it? Please, are you okay? So if you were to write a function in now to do the moment estimation, it's quite easy. We just put a function, let's say ESP mom is a function that takes x and then 1 over the mean. We get our estimate. Is everybody okay with it? Okay. What about the gamma? My friend. 3. Hurry up.
Set a gamma.
Hurry up and give me the moment.
So the moment, the
Okay,
first
so alpha cap will be what?
x bar,
X bar.
beta cap.
X bar what? Yes, it's all squared. Is that all? Over S squared. Are you sure? Okay, what about the beta? Whatever you say, I write it. You did 3, I was running. Yes. What about the beta?
X bar
X bar
over S squared.
over S squared. Okay. So we are assuming that this is true. So if it is true, then if we want the moment estimator for a gamma distribution, it means that we will write a function. That function will calculate the mean, the variance, and then our alpha cap will be S bar squared over S squared. Then our beta cap will be what? S bar over what? S squared. Is everybody okay with it? So that will give us our estimate. Please, I need you to pay attention here. So that's the moment. It's quite simple. And that you know it because we already know how to write a function. The next thing we have to do, I am so sorry. The next thing we have to do now is that of maximum likelihood. And please note over here. So, I need your attention. What is the principle behind the maximum likelihood estimation? So now you need to know the principle. What is the principle behind maximum likelihood estimation? Yes. Quickly, we don't have time, please. Otherwise, you get another assignment. That one is shared among all of you. Yes, yes. The probability that who else? The probability that the sample is part of the population. Who else? Yes.
You first assume that the sample is taken from a particular distribution.
Yes.
So you find the estimate that which will be the highest probability of getting that distribution. So you find
The highest probability of getting that distribution.
or highest probability of that distribution.
Yes, who else? So you have 3, 2 now. Who else? You want to talk? That satisfied the likelihood function. Yes. Yes. What is the principle behind maximum likelihood estimation? Yes.
So after assuming that it belongs to a particular distribution,
Yes.
you find an estimator which make the likelihood of it belonging to that distribution high.
have a point in there. Yes.
The MLE used to find for the sample parameters that are closely related to the population parameters.
That are closely related to the. Okay. Okay, you all have a point in there. So what happens is that I have x from some p theta, right? Okay. So I don't know theta. All I know is that x comes from a distribution p with parameter theta. Of course, theta can be k dimensions, right? Okay. Now, the principle says that we want to find the estimate. We know the parameter space, right? So we want to find the values of the theta caps or theta cap values that will maximize the likelihood. What maximizes the likelihood? It means that those theta caps will now give us, it has the highest chance of generating the sample that we have. And it turns out that such values will now be closely or be, will estimate what theta that we don't know. Okay, so what do? It means that if we have x, we need to find x generated from that distribution. We need to find the likelihood. How do we find the likelihood? It's a product of what? The densities for each of them. Remember here, our idea is that they are ID, right? Okay, so if they are ID, then we expect all of them to have what? The same distribution. Other than that, F1 will not be the same as F2 and F3 and so forth. Okay, and so forth. So if X and we have it has P, or let's say F of or F theta, right? So here what we are saying is that the likelihood function of, let's say, theta, given the sample that we have, right, will be the same as all. The product or the likelihood is a product of 1 to, let's say, k or n, if I should put it that way, then f of I of, f of xi, right? Because we say they are ID. If they are not ID, then our f1 may not be the same as f2 and so forth. Okay. Now, it turns out that we usually will use the log likelihood, right? And what is the, why do we use the log likelihood? So it means this will be, why? Why do we always prefer to use this and not that one? Yes. Yes. It's difficult to differentiate. And why do we differentiate? Why do you differentiate? Yes. Why? To find a maximum. Okay. Yeah, because we are saying that our theta should maximize this, right? Okay. So, in other words, our L of theta x, we want to find argmax of theta of this function, right? Okay. How do we find it? It means it's the same as finding the turning point, right? Okay, so we can then say that we maximize this, and how do you do that? We will set this to 0, we will differentiate, set it to 0, and that becomes finding the zeros of the function. Is that okay? So, but still, you haven't told me the reason why we differentiate. Sorry, we use this and not the other one. And then that results in what? Theta cap. Why do we use this and not that one? So you said that so the difficulty. Okay, so now we differentiating. What else? Dr. Issa's door is just here. Or we go and take back all the marks we added to your 333. So that you know that whatever you got, you come back to the next 2 grades below. Okay. All right, so the main argument is that whatever will maximize this function also maximizes that one, right? So if it is easy to deal with this one, then because this is monotonic, right? And so forth. So please take note of all those basic stuff. But in R, we are not going to do what you used to do in the 333. We come back to the basic definition of likelihood. That's why I've been asking you, what is the principle? So when we take a data set, we are not going to find S bar is the maximum likelihood. So you find the mean and that's it. No way, that's not how we do it. Please, are you following me? So we go back to the basic principle of the estimation, which says that we are looking for values of theta that will maximize the likelihood. In other words, we are looking for values of theta that will generate, that best generate the data that we have. So what do? We will take this likelihood and then we do some numerical methods. That means you need an optimization algorithm. So what you were doing in maths department, Newton's, this one you do it at SHS, Newton's method.
No.
You've not seen Newton's method before. But you've done math 223.
Yeah.
Even math 122.
One.
Secant.
No. It's out of the syllabus.
No, it's not true.
Yes,
It's not true.
Okay.
Okay. But it turns out that in R, is it time?
Yes.
It's time. 2 minutes. So what will happen is that we will need this log likelihood, right? And remember, the log likelihood is now a function. So for example, what is the log likelihood function for the, if x is Poisson? The Poisson distribution. So we have probability that x is equal to x e to the power negative lambda, lambda raised to the power x factorial, isn't it? And x stands for where to where. The Poisson distribution. 0 to good. 0, 1, 2, and so forth. Okay. Now, what will be the likelihood function? It means you have to take this sum to odd, or multiply it, and so forth, right? And then we find log. So let's find the log likelihood. Lambda x. This will be what? Sigma, right? Isn't it? Then the log of all that. Okay. So log of this will give us what? Negative lambda, right? Okay. Plus x log lambda. Then this will be minus log x factorial. Is everybody okay with it? Good. Okay. So you can now find, let's say, I moving from 1 to n. Sorry. Okay. Now listen. But if you remember this one, x log x, the data alone does not play any part. So in your score function, you can ignore x. This is 333. Otherwise, I call Dr. Isa. So, this is for negative n lambda. Do you agree?
Yes.
Okay. Plus, okay, so sigma x log lambda, then I can leave it there. This is not part. Why is it so? Because when you differentiate with respect to lambda, this one does not have any lambda attached, so it will be 0. So we are okay to go with this. So what you have to do is now to write a function in R, and that is your likelihood function. Is everybody okay? Okay, now this likelihood function, we are going to put it in an optimization routine. Now we use maybe the Newton's method, secant method, Neldami, simulated annealing, there are so many of them. Are you sure you people have not been doing those American methods? I don't believe. Okay. But this one you can do it, right? So it means that the function must take in, and that's the defect of the maximum likelihood estimation. Moment is easy. You don't need anything from the, all you need from the data is that you have the data and you have the moment. But likelihood, you need to always get a starting point for it. And that's what I need to do. I don't know the parameter. I just go and how do I get a starting point for the data? And so, but it turns out that we can do this. Okay, so lambda, the function, you write a function that takes in lambda. Of course, n, you can calculate it because of the x. Because that's the sample size. So if I put in it needs x and it needs what? Lambda. We can calculate what? N. So you have to write a function. Please do so for this when you go home. Okay. And then if you do that, study the help files for obtain. For obtain. Because this is one-dimensional, one parameter, it will prompt you to optimize as well. So these are the routines you can use to do this. And please go to the YouTube page and check on some of the videos I have done on maximum likelihood estimation. It's not difficult. So all you have to do, I've explained the principle why we do so, and I think you should be able to do the rest. Okay, thank you, and we meet next week. Any question? Okay, I have not sent you the, I'll do so. Did I, okay. All right. But did I add the script? No, okay. All right, so I'll put the script on Sakai, then you can